In this lecture, we're going to learn the parallel axis theorem and use it to determine the moment of inertia for a composite area. We know that the moment of inertia is calculated about a specified axis. When the axis is different, then the moment of inertia is different. The parallel axis theorem can be used to find the moment of inertia of an area about any axis that is parallel to an axis passing through the centroid, so which we call the centroidal axis. This theorem has many practical applications, especially when working with composite areas. So now let's take a look at an area is an arbitrary area here with a centroid C. We locate a centroid, and this centroidal axis, x prime and y prime, are the axes passed through point C. Our goal is to calculate the moment of inertia about the x-axis or the y-axis. So x and y-axis are any axis, arbitrary axis. So now the x-axis is parallel to the x prime and y-axis is parallel with y prime axis. And the distance between the corresponding axes are dy. Dy is the distance from x to x prime, since it's along the y direction, so that's why we call it dy. And same idea, the distance between y and y prime, we call it dx because this distance is along the x direction. So now the moment of inertia about the x-axis, which is parallel to and the distance dy from the x prime axis, is found by using the parallel axis theorem. And same idea, the moment of inertia about the y-axis, which is parallel to and distance dx from the y prime axis, can be found by using the parallel axis theorem as well. Now let's try to figure out the moment of inertia about the x-axis using the definition formula. So moment of inertia about a given axis is defined by the integral over the entire area r squared times dA. So r is the distance from the differential area dA to the axis. Now, based on this given area, we're going to pick an arbitrary differential element dA. And the distance of dA to the x-axis, again, we are looking for, right here, find I about x. So the distance from dA to the x-axis is y. In other words, in this formula, definition formula, this r for the given area is y. And now, if we're going to plug in the r value into the I of x equals to the integral over the entire area of y squared times dA. And we can rewrite y in terms of y prime plus y dy, where y prime is the distance of the dA to the x prime axis, and the x prime axis is the centroidal axis. And dy is the distance between x and x prime. So we can also find this y equals to y prime plus dy. So let's substitute y prime plus dy into the equation here. So we have y prime plus dy squared times dA. And we're going to expand this term now. And we're going to separate the integral parts. And this is what we have. Now pay attention to the different terms. And since dA is a differential element, and we can choose this differential element at different locations. So this y prime, the distance between the dA and the x prime axis is a variable. So y prime is a variable. But this dy, so dy is not a differential y, is not a differential term y, but is the distance between x and x prime axis. So when we have this area, x prime is fixed, and when we have this arbitrary x-axis is fixed. Therefore, the dy term is a constant. So now let's simplify those integrations by bringing the dy term out of it. So after we bringing the constant terms out of the integration, this is what we have. Now let's take a closer look at this I of x expression to see if we can further simplify it. First, let's take a look at this point C. Point C is the origin of this centroidal axis, x prime, y prime. And since we build up this x prime, y prime coordinate system by let them pass through this point C. So C is the origin. Therefore, the location of point C or the coordinates of point C, if we use x prime bar and y prime bar, since now we have two coordinate systems, x and y, so this prime means that's the centroidal axis. So the point C, coordinate of point C in the x prime, y prime axis or coordinate system are 0 and 0. Since again, C is the origin of x prime and y prime coordinate system. And now, based on the definition of centroid, if we are looking for y prime bar, using the definition y prime bar equals to the integral of distance of dA to the axis, x prime axis, which is y prime, times dA divided by the integral of dA. And now we said y prime bar equals to 0. That means this whole expression equals to 0. And since the integral of dA, which will be the area, should not be 0, so the top expression, the integral of y prime times dA, must be equal to 0. So that means if you take a look at the I of x expression, that middle term we have 2 times dy times this integral part, and this integration equals to 0. Therefore, this entire expression should be 0. And next, let's take a look at the first expression, the integration of y prime squared times dA integrate over the entire area. If you recall the definition of moment of inertia, I about a given axis equals to the integral of r squared times dA. Now this y prime term is the distance from this dA to the x prime axis. So based on the definition of the moment of inertia, this first expression integration is the moment of inertia about the x prime axis. So it's x prime axis is the centroidal axis, so we give it a special special symbol, which is the bar on top. This means is the moment of inertia about the centroidal axis. So I bar, okay, I x prime bar, moment of inertia about the x prime axis. So you can write that. This is the moment of inertia about the centroidal axis. Now the third expression, the integral of dA will be the area a and dy is a constant. Therefore, we can have dy squared times a. So is a constant term. Therefore, I of x, the moment of inertia about any given axis, which is parallel to the centroidal axis x prime, equals to the moment of inertia about the centroidal axis I bar plus d squared times a, where dy or d is the distance between those two parallel axes. And using the similar approach, we can find the moment of inertia about the y-axis, which equals to the moment of inertia about the centroidal y prime axis plus d squared times a, where d is the distance between the two y-axes. And again, I bar x prime is the moment of inertia about the centroidal axis x prime, and I bar y prime is the moment of inertia about the centroidal axis y prime, and those values can be found from the table or are already given in the table. So the moment of inertia for an area about an axis is equal to its moment of inertia about a parallel axis passing through the area's centroid plus the product of the area and the square of the perpendicular distance between the axes. Again, when we apply this parallel axis theorem, thus I bar x prime or I bar y prime must be the moment of inertia about the centroidal axis. So it's applied between the centroidal axis and another given axis. So it's not between any two parallel axes. Okay, one of the axes must be the centroidal axis. Also in this equation, d of x is the distance between y and y prime, and dy is the perpendicular distance between x and x prime. A is the total area. Therefore, d squared a must be a positive value. So I bar plus a positive value. So the result is always greater than or equal to the I bar value. Therefore, we say this moment of inertia about the centroidal axis, I bar is always the smallest among any parallel axes. And since we can understand or we can interpret this moment of inertia is the resistance to rotation. So if the area rotates about its centroidal axis, it will provide the minimum resistance. To help us understand this statement, we can think of a ballerina, and she is rotating or she's spinning. It will be much easier for her to spin about her own centroidal axis, the axis passed through the center of the body, than if she is spinning about an axis that's outside her body or far away from the centroidal axis. Now, the area moment of inertia about the centroidal axis can be found from the back cover of the book or the appendix of the book. You can also find it from Canvas page. I uploaded this page there. So if you take a look at this rectangular area, right, the I of x, that's the moment of inertia about the centroidal x-axis. Make it bigger. Equals to 1 over 12 times b times h to the third power. So b now is the width or length of the side that is parallel to the axis, and h is the side that is perpendicular to the axis. Same idea for I of y. The moment of inertia about the centroidal y-axis is 1 over 12 times h now, hb to the third power. So again, you just need to remember is the side b is the side that is parallel to the axis, and the other side will be the to the third power. So again, for the y will be h times b to the third power. Okay, now let's take a look at one example. So if we're looking for the moment of inertia about this given x-axis, which x is along the bottom side of this rectangle. So first we need to find the centroid, or the centroidal axis x prime, which should pass through the middle center of this area. I'm going to draw it. This is the centroidal x prime axis, and the distance between the two axes are half of h. So to find the moment of inertia about the x-axis, we use this formula, I of x equals to the moment of inertia about the centroidal axis, I bar x prime plus the distance between the two axes squared times a. And now we figured out all the terms, and based on the formula or from this table, we know that moment of inertia is 1 over 12 times bh cubed. So we just need to substitute the numbers in. 1 over 12 times b times h to the third power plus the distance between the two parallel axes are h over 2 squared times the total area, which will be b times h. And we can rearrange and simplify the results. And this is what we have. 1/3 of b times h cubed. So you can see the unit of the moment of inertia is the length to the fourth power. And now if we move the x-axis above, so now it's 1 or a quarter of the height, away from the bottom, which is h over 4. Let's find I of I, the moment of inertia about this new x-axis. And same idea, we still use the equation I of x equal to the moment of inertia about the centroidal x-axis plus the distance between the x and x prime times the area A. The only difference now is the distance between the two axes are changed. It's from 1/2 of h to 1/4 of h. And we can substitute values into this formula. Just change h over 2 to h over 4, and the result will be 7 over 48 times b times h to the third power. So how about if you have another x-axis which is above the centroidal x prime axis, but the distance is still h over 4 from x prime. What is the moment of inertia about this x-axis? Let me call it x1 axis. So moment of inertia about x1 axis. Do I need to do calculation? Think about that. So again, based on this formula, the moment of inertia about the centroidal axis doesn't change. It's always the same value for the same given area. And A doesn't change as well. As long as the D, the perpendicular distance between from this given axis to the centroidal axis is the same, then the moment of inertia about that axis will be the same as well. Therefore, because the x-axis and x prime or x1 axis are symmetric about x prime, they have the same distance between the corresponding axis and the x prime axis. Therefore, the moment of inertia about those two axes are the same. So what is the purpose of defining this parallel axis theorem? Where can we apply it? Well, cross-sectional areas of structural members are usually made of simpler shapes or combination of simpler shapes. Like this T-beam, we have two rectangular shapes. One is horizontal, one is vertical. And to design these types of members, it is required that we define the moment of inertia. And then we can figure out the stress distribution over the cross-sectional area. So it is helpful and efficient if we can do a simpler method to determine the moment of inertia compared to the integration method. And this is another example of a structural member with a composite cross area. Such assemblies are often referred to as a built-up beam or member or a composite area. So design calculations typically require the use of moment of inertia for these cross-sectional areas. Again, we need to have moment of inertia to determine the stress distribution over the cross-sectional area. So the parallel axis theorem made it possible for us to use a simpler method, which is very similar to the composite area method we used earlier to find the centroid location of a composite area without using integration. So again, let's review what is a composite area. So a composite area is made of adding or subtracting a series of simple shaped areas like rectangles, triangles, and circles. And then we can use in the moment of inertia about their own centroidal axis, which we already have those values from the table, and then apply the parallel axis theorem to find moment of inertia about this entire cross-sectional or composite area without using integration. Simply speaking, if we have an infinite number of differential elements, to get the sum, we have to perform integration across the entire area A, and based on this I of x, definition will be y prime times dA. But if we have a finite number of elements, we do not need to apply the integration anymore. We just need to get the algebraic sum of y squared times a, and then apply the parallel axis theorem. It equals to the sum, algebraic sum of I bar x prime plus d squared times a. And I bar x prime is the moment of inertia about its own centroidal axis, and d is the distance between the centroid of each area and the x-axis, and a is the area of each sub-element. Let's take a look at one example. We have a beam which has a composite cross-sectional area, and we're looking for the moment of inertia of the area about the x-axis, and x is in the middle of this beam. And follow the steps for analysis. Let's develop the steps we need to follow using this example. So just the same idea as we looking for the centroid of the composite cross-sectional area. First, we need to divide this composite area into smaller or simpler shapes. And we can divide this cross-sectional area into 3 rectangles, and we label them with number or letters. So here we have 1, 2, and 3 rectangles. And then we are going to apply the method we just developed, or we're going to apply that formula I of x equals to the algebraic sum of I bar x plus d squared times a. So let's put those values in the table to help us do the calculation. And keep in mind, this I bar x prime is the moment of inertia about each area's centroidal axis. And now we have 3 rectangles, and we know for rectangles, the moment of inertia equals to 1 over 12 times b times h to the 3rd power. So let's put a table here. Label each segment. We have segment 1, 2, and 3. And first, let's locate their own centroidal axis, or centroidal C, and find the distance d between the C and this x-axis. So for the first area of number 1, this rectangle, the centroid is located here in the middle of in the center of the area. So if we call this C1, so we know x passed through the center of the cross section, therefore it's to the top of the cross sectional, or to the top of this beam, the distance is 150 plus 50, which is 200 millimeters. And now since C is located in the middle of the top horizontal rectangle, so the distance of C to the top is half of 50, which is 25 here. Therefore, from this point C to the x-axis, if we call this D1, and we're looking for the centroid of each area to the given axis. So this distance is the D we're looking for, and this D1 is 200 minus 25, which is 175 millimeter. So then we can put it into this table. D1 is 175, and the unit is millimeter. For area number 2, the centroid is in the center, and since x-axis passes through the center of the overall, which is also the center of the second area, this is C2. Therefore, the distance between C2 and the x-axis is 0. And next, area number 3. So area number 3 is the same as area number 1, and those two areas are symmetric about the x-axis. Therefore, it has exactly the same value here as area 1, which is also 175 millimeter. Next, let's find the areas A. So A1 again should be equal to A3 times 50, equals to 50 times 200, and this is 10 to the 4th power millimeter to the 4th power millimeter squared. And then area number 2 equals to 50 times height is 300, therefore is 1.5 times 10 to the 4th millimeter squared, and then we're going to put them into the table as well. And next, we're going to calculate let's find the moment of inertia about their own centroidal axis. I bar x prime using the formula here, which is available from the table, 1/12 times b times h cubed. And same idea, this I bar x prime 1 and I bar x prime 3 are the same. They will be equal to 1/12 times b. Well, it seems like we should have b and h listed in our table as well. Then it will be much easier, isn't it? So now again, b is the side that is parallel to the axis, which will be 200 millimeter. So that's the b side. We're going to do the 200 millimeter times h. H is the other side, which is 50 millimeter. 50 millimeter to the third power, which equals to 2.08 times 10 to the 6th power, and unit is millimeter to the 4th power. And then we can calculate I bar x prime of the second area, which will be the same formula, 1/12 times b, and this time the b is this smaller or shorter side, which has a dimension of 50 millimeter, and the height is 300 millimeter. So times 50 millimeter times 300 millimeter to the third power. And the result is 1.125 times 10 to the 8 millimeter to the power 4th, and then we're going to put them into the table as well. So we can put the unit on the header of the table. Next, let's get d squared times a, which will be the first column times the second column. And the unit, since d squared has unit of millimeter squared and times millimeter, another millimeter squared, which will be the millimeter to the 4th power. Well, I think I made a mistake over here. It's not d times a, but it should be d squared times a. So it's 175 squared times 10 to the 4th power. So the value is 3.06 times 10 to the 8th power. And it has the same value as for the area number 3, which is also 3.06 times 10 to the 8th power. And for area number 2, since d is 0, so d squared over a, or d squared times a, is also 0. And now we can add those two values together. I bar x prime plus d squared times a for the corresponding areas. So we're going to add this column. Here's a different color. And the column here. Add the corresponding values. So for area number 1 and number 3, when we add the I bar x prime and d squared times a together, we will have 3.083 times 10 to the 8th power, and here as well. For area number 2, we have the same as the moment of inertia about its own centroidal axis, which is 1.125 times 10 to the 8th power. And the unit I'm using here is millimeter to the 4th power. You can also convert it to meter to the 4th power, but please do indicate what units you are using for your solution. And next, for the overall moment of inertia about the x-axis, we have to add those terms together. So the sum is just adding the three values together, which equals to 7.0 291 times 10 to the 8th. Unit is millimeter to the fourth power. So this will be the result we are looking for, which is the moment, error moment of inertia about that given x-axis, which passes through the middle or the center of the entire cross-sectional area. Now let's summarize the steps for analysis. Step 1, we divide the given area into simpler shaped parts. In this given example, we're going to divide the entire cross-sectional area into two parts. One is a rectangle, one is the circle. But since the circle is a whole, therefore we have to perform subtraction instead of addition. Step 2, locate the centroid of each part and indicate the perpendicular distance from each centroid to the desired reference axis. So in this example, we're looking for the error moment of inertia about the x-axis given here. Therefore, we're looking for the distance from each centroid to this x-axis shown here. Number 3, we're going to determine the moment of inertia of each simpler shaped part about the desired reference axis using the parallel axis theorem. This is the formula, and where I bar x prime is the moment of inertia about its own centroidal axis for this rectangular area and the circle here. And this I bar x prime formula can be located from the table, where you can find from Canvas or from the back cover of your book, times the product of d squared times a. The d is the perpendicular distance we figured out from step 2. And the last step, the moment of inertia of the entire area about the reference axis x, is determined by performing an algebraic summation of the individual moment of inertias obtained in step 3. And also, if we have a hole here from the cross section, we have to perform subtraction instead of addition. Couple of important points you need to keep in mind when using this parallel axis theorem. First of all, the parallel axis theorem for an area is applied between an axis passing through its centroid and any corresponding parallel axis. Second, the moment of inertia of a composite area equals to the algebraic sum of the moment of inertia of all of its parts.